210 kilometers an hour, and the country was transformed. Dr. Eiji Nakatsu was general manager of the technical development department.
In 1964, after the opening of the Tokaido Shinkansen, we could have so many passengers, tourists, and business trips. The airline between Tokyo and Osaka was demolished, and the motorways utilization was also temporarily decreased.
The 515-kilometer journey between Tokyo and Osaka in the Tokaido Shinkansen was now possible in just 4 hours, as opposed to the previous 6.5 hours. But it wouldn't take long before Japan wanted to go even faster.
The first of the beginning of the Tokaido Shinkansen, the maximum speed 210 km per hour. After that, we have tried to realize the speed up to 120 km per hour or 270 km per hour.
But increasing the speed of these super trains created an unexpected phenomenon.
When our train goes rush into the tunnel with high speed, the shockwave stand up and go to the exit of the tunnel. And on the exit, we can get a big bang, dogan, like that. And also, this pressure wave spread in all directions.
Like a piston in a cylinder, as the train sped into a tunnel, it generated atmospheric pressure waves, forcing the air out of the tunnel exit at the speed of sound, creating what's known as tunnel boom.
For the people on the line, these noises became a big problem because from 6 o'clock in the morning, early morning until midnight, they were suffered from these noises.
Homes as far away as 400 meters were affected by the ceaseless noise. And if trains were to go faster, it would only get worse. So how do you keep up with the demand for more speed and at the same time reduce the noise pollution? The answer came in the form of the newly designed 500 series. Designed by Dr. Nakatsu, he created a revolutionary new shape inspired by nature.
I am a bird watcher. My hobby is bird watching. Kingfisher jump into water to catch game from the air with lower resistance and into water with higher resistance. This is very similar to the train set rush into tunnel. That gave me a good idea.
A kingfisher dives into the water at high speed, and even though water is 800 times denser than air, it barely makes a splash. The kingfisher's streamlined success lies with the shape of its bill.
I realized that kingfisher could be a good inspiration for our head shape of the Shinkansen trains.
The new 15-meter nose cone almost exactly replicated the bird's bill shape, producing remarkable results. Introduced in 1997, these new super trains had 30% less air pressure resistance and could reach the record-breaking speed of 300 kilometers per hour. And the tunnel boom was dramatically reduced. It was a major breakthrough in fast train engineering, setting a template for the future.
This project was not made by myself. So many staffs of the personnel worked together for this project. And I am proud of it. And this train set 503 gave a good influence not only Japan but also all over the world.
The bullet train is an undisputed high-speed icon. Since 1964, it's been refined several times over, getting quicker each time. But the latest bullet train engineers have turned their attention to the fastest technology of all, maglev. Still in its trial phase, the new magnetic levitating bullet train has surpassed 600 kilometers an hour. This frictionless train hovers above the guideway and relies upon the properties of superconductors for its extreme performance. Physicist Andrew Steele explains.
A superconductor like this one is a material that has no electrical resistance when it's cooled below a certain critical temperature. So when we get this down to minus 200 degrees, it's going to conduct electricity but without losing any energy. So if I drop it into nitrogen, that's cooling it down to that incredibly low temperature. When you bring it near to the magnets, it sets up an electrical current inside the superconductor, which keeps it levitating there. But that electrical current is stopped as soon as the superconductor gets above that critical temperature.
But if the superconductor remains cold in its superconductive state, the current will continue to flow almost indefinitely, creating an intense magnetic field.
We can use a principle very similar to this to try and make an example of a frictionless transport system. Here we've got some liquid nitrogen again. We just pour the nitrogen onto the superconductor, and because the superconductor is being cooled down really close to those strong magnets, it memorizes the magnetic field that it's cooled down near. And that means that it wants to stay in the same position relative to those magnets. So since the magnetism is the same all the way around the track, that means that it'll be stuck to this particular path. If I give it a little push, it'll go around and around for a very long time. So you can see that this kind of electromagnetic levitation with superconductors allows us to create a friction-free transport system.
And it's this friction-free technology that allows the Japanese maglev to break records. On board, superconductive magnets cooled with liquid helium to minus 269 degrees Celsius are used to both levitate and propel the train. It's hoped service will begin in 2027, with eventual travel time between Tokyo and Osaka just over an hour. A far cry from the 6.5-hour rail journey of the past, once more securing Shinkansen's status as fastest in the world.
I think the Shinkansen are the most iconic railways on the history of the railways.
Achieving and maintaining great speed means balancing great forces.
When you have a train very powerful and very light, you need a special balance between grip and power.
Pushing rail engineering to its limits.